Alright guys, we're going to get started. So, for those of you that came in late, so my name is Tyler, this is Soraya. We're going to be co-teaching this review today. So for those of you that came in late, just know that these reviews, so it's for 2 hours, but you only need to stay for 1 hour because in both hours of the review we're going to teach the same material. So if you only want to stay from 6 to 7, then that's fine. You can stay for both, but just know that both hours will have the same material, so there's going to be nothing new. So we're just going to get started. So our review, we're just going to go through chapter by chapter, and then we'll just talk about the key concepts that each chapter has and just the things that you guys need to know. We don't have a whole lot of practice problems to give you because we believe that understanding the concepts will help you solve any problem. Okay, so before we get started, is there any questions? Okay. So chapter 16. So one thing important about chapter 16 is conjugation. Right? Conjugation is where we have a contiguous array of pi. Oh, gotta make sure I get away from that. A contiguous array of pi atoms spread across the molecule. So it would be something along the lines of this, right? Where we have two double bonds and just a single sigma bond in between them. Something like this, or this, is not conjugated, right? Okay, and so another thing to remember about conjugation is the reason conjugation is so important is because it delocalizes the electrons, lowering the energy of the molecule. And so one thing to remember though is for every atom that's in a conjugated molecule, the bonds are shorter. The sigma bonds are shorter than regular sigma bonds, but not as short as double bonds, and that's because of the delocalization, the resonance that spreads out, that gives every bond a double bond character. Okay? So the next thing is pi orbitals. So the number of pi orbitals coincides with the number of electrons in a system. So with this 1,3-butadiene, it will coincide, so it has 4 pi orbitals and 4 electrons. So it's going to have 4 pi orbitals like so, right? And so that's important to remember that as with pi orbitals, as we go up, we're increasing our energy, and that the more pi orbitals or the more conjugated a molecule is, the closer together those pi orbitals are. Okay? You always fill an electron starting with the lowest energy and going up. Right? This is common stuff. Does anybody have any questions? Anything? Okay. So the last thing is we're going to start reading. Oh, what's up?
So, why do we need to know that they're close together? Why does that matter? Where does that apply?
So this will apply in things like when we're dealing with light and energy. So when things are coming together, so say we have, so this is really big in eyesight. If you remember with Dr. Price, when he was showing us this molecule was really conjugated, having this shorter homo-lumo gap right here allows for us to be able to see the visible light region. That allows for, because right now this molecule we can't see, but those molecules that have shorter homo-lumo gaps, we can see those, and those are in the visible light region. Okay? Okay, so now we're going to get into the Diels-Alder. The Diels-Alder is an important reaction that we do in organic chemistry. Some of the things to remember is that when we do a Diels-Alder, we're forming a ring. So we're always going to form a ring. It's an addition reaction, so in chapter 30 we learned about cycloadditions. The Diels-Alder is considered a cycloaddition reaction, but it's only done under thermal conditions. There's no photochemical conditions that are done with Diels-Alder. So that's something to remember, and that's important. And one thing with Diels-Alder that's also important to remember is that you have, with your diene, it has to be in the cis. You can't do a Diels-Alder reaction with your diene being in the trans configuration. That's because when we have it in the trans and we bring in an olefin, or a dienophile, excuse me. When we bring in a dienophile, it's those 2 double bonds right here. So see how this is trans? If we were to bring a dienophile from this side, then it can't connect with this, and we can't have our 4+2 cycloaddition. So that's why this diene has to be in a cycloaddition, or in a cis conformation. Another thing to remember is we're using the pi homo-lumo gaps, and that's because when this reaction comes, when we have something like, so a simple reaction to follow is if we have something plus this, then we need to make sure that we're using the homo-lumo gaps. Excuse me. Right, so the homo gap here and the lumo, or sorry, that's right. So the homo gap here or and the lumo gap here, that's where the reaction is taking place in Diels-Alder reactions. Okay, those are some important concepts to remember. Another thing you need to remember is, okay, so these are the rules of the Diels-Alder reactions. So this is what will constitute Diels-Alder. We have to make sure that when we do a Diels-Alder that we are following each of these rules. So first of all, it has to do via thermal, right? We're forming a 6-membered ring. We're going to break 3 pi bonds and then form 2 sigma bonds and another pi bond. And then it's done concertedly. So we're not forming any carbocations, we're not having any hydride shifts or anything along those lines. So Diels-Alder, there's some certain things that we need to remember with Diels-Alder reactions. The 2 main things, diastereospecificity and regioselectivity. So if we have a reaction, so say we're looking at this reaction and we have it being cis like this. Okay, so we have this reaction, it's cis. Then we have to make sure that when we form our products, it's cis as well. Right? Okay. And then if it's trans, so if I were to draw this and take it and make it like that, and make it a trans molecule, then we make sure our 6-membered ring has a trans substituent as well. So one hint that I found when doing these reactions is if you look at if you're looking at the substituents, so right here and right here, and if you look at what's on the outside versus what's on the inside, the outside substituents should always have the same stereochemistry, and the inside substituents should always have the same stereochemistry. So for this reaction, this methyl group and this hydrogen should both be cis to each other, while this hydrogen and this methyl group will both be cis to each other. Okay, does that make sense? Is there any questions regarding that? If you guys have any questions at any time, just stop us and raise your hand or something, and we'll be happy to answer those. And then the other important thing about Diels-Alder is electron withdrawing and electron donating groups. And that'll change, that goes with the regioselectivity depending on when we form a 6-membered ring, where is that molecule going from? Like whether it's going to form ortho, para, or meta to the dienophile. Okay? So keep those in mind as you're studying for your test. Yeah?
So on that example on the board, I just want to make sure I'm seeing this right.
Right.
If the olefin came in from the bottom, the hydrogen inside and the methyl group inside will go up, right?
Yeah, they're just, like whether it comes from the top or the bottom, the methyl group on the inside and the hydrogen on the side will have the same, they'll either be up or they'll be down.
Okay.
They just have to have the same stereochemistry. Yeah, good question. Any other questions? Yeah.
Is that for like endo and exo? Are you gonna get that or?
So Dr. Price said not to worry about that, so we're not going to cover it. Yeah.
So we were trying to draw all the products. Typically, if you came from the top and bottom, that makes the same product.
Yeah. So that's why I said, like, whether you come from the top or the bottom, they're going to be cis, so it doesn't matter where you come from. You just have to make sure, the important thing to remember is you have to make sure that they are either cis or if they're cis, they stay cis to each other. If they're trans, they stay trans to each other. Right here?
That had groups on it.
Mm-hmm.
You could get coming from the top to bottom distance.
No, not really, because if you have something like that, then you have to make sure that they stay trans. Or are you thinking like endo and exo? Yeah, so don't worry about endo and exo because Dr. Price has made it clear that he's not going to test you guys on that because he says, while it's important to know, he says it's not something that is vital for you guys to know. Okay? Okay. So here's some practice problems to give you guys some kind of ideas. So I didn't take Dr. Price when I took Chem 352. I took a different professor, and so he said it would be okay if I used some of his practice problems from the test he gave me. So this is one of them. So what you want to do is take 1,3-butadiene and compare it to the molecule right there with the arrow. So this molecule right here, which is called rhodopsin with an imine. And so what you want to do is you want to compare the orbital diagram, the two molecular orbital diagrams that these two molecules will have. Meaning showing, like if you were to draw so if you were to draw 1,3-butadiene, right, like that, then you're going to want to show like what its orbital diagram looks like. And then do the same thing with rhodopsin. And that's a practice problem for you guys to kind of get you comfortable dealing with orbitals and how, yeah.
You always compare the HOMO, the butadiene, and the LUMO,
The olefin on Diels-Alder. Yeah. So say with the Diels-Alder, if we have something like this, right? And so we're going to fill up, because we have 4 pi electrons, so we're going to fill up to the second pi orbital. And then same thing, if we're reacting it right here with just a regular ethene, then we're going to just fill up right there. And yeah, so we'll compare it. Here's our LUMO here, and here's our HOMO here. And what we want to make sure is that our orbitals are matched up, right? So if this is C2, then we want this one to make sure this one's C2. And make sure that our in-phase orbitals can overlap with each other in order to form those bonds.
And can you switch those? Can you do LUMO and then?
Yeah. Is there any other questions on Diels-Alder? Yeah.
When you use a big molecule like oxygen, how do you determine where, like you attack, like which olefin?
Okay, so for like for a reaction like this, I'm not sure how the Diels-Alder. I don't think there would be necessarily. I mean, I'm sure there would be a Diels-Alder, but I don't know how to go about it. This is more just showing, like getting you comfortable showing like how conjugation and drawing those molecular orbitals goes. Like understanding how as you get more conjugated, those HOMO-LUMO gaps get smaller and smaller together. That's the point of this problem. Yeah.
So are we supposed to draw like all 12 here and C2 orbital configuration?
No, so the purpose of this problem is, so I'm not going to draw it, I'm just going to write R for rhodopsin. What you want to show is that as you get more conjugated, see how the HOMO-LUMO gap here is really big? As you get more conjugated, that HOMO-LUMO gap gets smaller and smaller. And that was the point of this question. Yeah.
Could you go over again, Tyler, just how you can tell when it'll be smaller or greater?
So yeah, just the more conjugated the molecule gets, the smaller those HOMO-LUMO gaps.
So there's no way like track like that. It's just like kind of just.
It's just like a trend.
It's like a trend, okay.
It's like electromagnetism. It's a trend that you can follow. Yeah.
Can I ask, so I know rhodopsin has more conjugated double bonds, so it's smaller gaps.
Right.
And that allows for visible light to be reflected.
Yeah. So rhodopsin will show up. Its energy will allow it to be seen in visible light. So instead of being a clear solution, it'll be like purple or something like that. Okay. So does anybody have any questions with rhodopsin? Yeah.
Would you just quickly draw the molecular orbital diagram for rhodopsin?
So it's just right here. So it has 1, 2, 3, 4, 5. So 5. So it should have 10 electrons, right? So 1, 2, 3, 4, 5, 6, 7, 9, 10. And then like that. So here's the HOMO, and here's the LUMO. And then it'll have orbitals go along with that along with nodes.
So you don't count the double bonds?
No. No, yes you do. Sorry, yes you do. Yeah, sorry. That's my bad. Excuse me, guys. Yeah, I can do that. Yeah.
So being in a ring doesn't affect the concentration?
No, because so even though that double bond is in the ring, so his question was, does being in the ring affect conjugation? And the answer is no, because even though it's in the ring, it can still, through resonance, it can still delocalize all throughout the entire chain of the molecule. Okay, is there any other questions about rhodopsin or drawing these molecular, like this orbital diagram and the levels, like the pi tiers? Yeah.
So the double bonds in the nitrogen count.
It does count. That was my bad. So. I think we have one more. Okay, and so this is just a quick Diels-Alder reaction. Are we good on time, Soraya? Okay. So this is just a Diels-Alder reaction. So this question is, so identify the olefin, or the diene or the olefin, and then identify the dienophile, and then do the Diels-Alder reaction. And then this problem also helps you guys get practice with drawing the molecular orbitals to prove, because what I found is, and when we do these reactions, especially cycloadditions, it does no good to kind of try and skip steps and take a shortcut way, because a lot of times that's where mistakes happen. And so with this one, what you're trying to prove is, this is obviously going to be a 4+2 addition, and most of the time 4+2 additions go via thermal reaction. And so what you guys are trying to prove is, why doesn't it go via, say, a photochemical reaction? Okay, as well, like showing through the Diels-Alder reaction, like doing the entire reaction, drawing the molecular orbitals, showing why it doesn't go through a photochemical reaction. Yeah.
But you can't have with this all the rest.
It has to be thermal.
So
And
are we reacting the bottom and the top?
yeah, so those are the two molecules you're reacting with. Okay, has everybody at least gotten this far? Or does anybody have any questions at, like, why have I got to this point? Yeah.
Why do you have two energy levels for the 1.6 or 8?
Because what you're going to come to see is that the reaction is a 4+2, and that the 2 pi electrons comes from this section right here.
Oh, the only.
Yeah. products for this reaction. Okay, and so then the final product for this reaction, right, so okay, so that's the final product. Does anybody have any questions as to why that's the product or where we got there? Yeah.
So would you not, you can't,
No. Because with this, sorry, why wouldn't we be able to write?
You don't use no folder instead of benzene because it would break every system.
okay.
Yeah.
Yeah.
The methyl group and the benzene ring means
These, they're going to be meta, and then that's a good question. So the question was, can they be meta or are they always going to be para? So I didn't draw the second product, but that's right. There will be a meta product as well. Excuse me. Okay, that's also a viable product. This one just formed because of the. It just comes because of the electron domains, right? The regioselectivity. Sorry, took me a second. So does anybody have any questions?
Is one of those preferred?
I don't think either one's preferred. I think they're both pretty show up pretty often. Yeah. Okay, and then okay. So yeah, and then here's like a little meme just to kind of show like Deals Alden would be proud.
First things first, I just have to say, I'm so excited about this robot thing. I know that it's so lame, but I'm so excited about it. Okay. How are we doing? Other questions on Diels Alder? We good? Just to reiterate as well, whenever you're doing Diels Alder, please remember that what he's going to get you on here is stereochemistry, okay? Totally, always, every time. He will not just give you A through D, he's going to give you A through E or A through J, okay? So there's going to be plenty of options for which you can get tripped up. So please make sure that you're focusing on stereochemistry. Yeah, these two right here.
So in the practice problem that we did, can they bond together always if it's two mirrored, like if the LUMO is mirrored and the HOMO is mirrored, or C2? If they're the same, can they, or is there times when they both could be mirrored but they still won't?
Like, what do you mean? Like doing a 4 to 2 or any cycle addition? Cycle addition occurs because there's matching. So anytime there's matching, there's going to be a cycle addition that occurs. But the things that you guys have seen are things in the book like 4 to 2, 4 to 6, or 2 to 2 with photochemical. So just make sure that you understand why those things are occurring and be able to see the orbitals. Another thing that he can test you on with orbitals is probably going to be a question where there's a bunch of orbitals drawn in, and he's going to give you a conjugated molecule, and he's going to ask you for the HOMO or the LUMO of that molecule. So you'll have to understand how many levels you need, where to fill in your electrons, and then to see how many nodes you have. He won't draw the nodes in, but you should be able to see them by when the orbitals switch phase. Yeah.
How close would you say his practice test is to his actual test?
It's pretty close. He structures it free response so that you can get comfortable doing the test that way. I would definitely do the tests as if it's free response, just because if you have any partial work on there that's correct, but you get the wrong answer, you might be able to get some partial credit back. So show all your work. Yeah. Yeah.
Is he another view above A and C?
I don't remember him doing that. He's pretty like straight to the point. There are some none of the aboves that he does. He also does some like why is this the case, like A through D and different sentences. So yeah.
So was this the correct stereochemistry then, or is it
So you actually don't have. How do I do this later? Can I do this? Okay, so for this one, there is a substituent. So I guess you could do an up or down for this if you want. But you can go on the top or the bottom. So, and there's only one substituent. So you could, I would probably do it just to make sure. Another thing I wanted to say about Diels-Alder really quick, I'm trying to go really quick, but anytime you do a Diels-Alder, a really good practice would be to always react to your olefin or your dienophile coming from the top or the bottom, and then flip one of the molecules and do it again. Because that way you can, and then look at your molecule and see, did I make the same product over and over? If you didn't, then they're diastereomers and enantiomers of each other. If you did, you don't have to include it. Does that make sense? Like, these molecules, they're basically reacting like this. And if there's substituents on this one and substituents on this one, for example, if you stick them up like this and you have them react together, this molecule could very well be like this, coming in the same way, or from this side. Does that make sense? So you need to consider all possible options, all possible stereochemical options. He will give you questions or answers that are only a few of them. So make sure you can you can do all of them, okay? Don't go into the test thinking that if you know how to do some of them and you've been missing some of the homeworks that you can just go in and recognize them, because you will get the question wrong, okay? Okay, that being said, let's go into 30. Okay, there's a lot of words on my slides, but it's just because I talk a lot, so it helps me to stay focused. Okay, ring opening. Always remember, when you're doing a ring opening, you always empty the sigma bond electrons from the sigma bond you're breaking into the LUMO of the pi system of the closed ring. Okay? So if you have 2 pi bonds in your closed ring, and you're opening the ring, you are doing 4 levels in your orbitals. And I like to do a little like shorthand. I've shown my students this in my recitation. But if I have a 4 pi electron system, you can do this with any number of pi bonds. It's what he was doing. It was what Tyler was doing up here. Any one of these questions, this is the very first thing I do every time on his tests. And it really, really helped me because no matter what question he asked, I was able to answer it with things like this, okay? So get comfortable with the shorthand. That way you do not have to draw every single orbital every time. You only really have to reproduce that on questions where he asks you what's the LUMO or what's the HOMO and show me the orbitals. Otherwise, you can pretty much get away with just understanding what the orbitals on the outsides look like, which is why you have these, okay? Remember, when you are opening the ring, you're going to have a different pi system than the pi system you started with. So I've had a lot of people who've asked me, well, I'm moving my pi bonds, but those carbons where the pi bonds should end up have out-of-phase orbitals. But they're out of phase in the pi system that you're working with in the beginning, but they will be in phase with your new pi system that you make when you open it. Does that make sense? Questions on that? So don't get confused by if you draw all the orbitals and realize that the pi bonds that should be formed at the very end are out of phase in that specific drawing. When you make the new product, they will be in phase for that new HOMO. Okay? Okay, questions? Good? Okay. Ring closing. You close using the HOMO of the pi system of the open ring. Okay? If you keep that in mind and get good at something like this, you'll be fine on any of these questions. Yeah?
To what extent do you think we'll need to know the disrotatory, photochemical versus like rotatory, thermal, all like the intricacies of that?
Very, very detailed. That's how he'll ask those questions. He'll ask you, there's 3 different types of ways he can ask the question. He can give you the conditions and the reactant and say, what's the product? And you'd have to find it in the answers. He could give you the conditions and the product and ask the reactant, or he could give you the reactant and the product and ask the conditions. And you'd have to figure out if it was conrotatory or disrotatory, was it thermal or photochemical. If you know how to do this and are able to draw the like the very last pi on each side, you can do conrotatory and disrotatory every time, no problem. Okay? So, that's why I say get good at something like this, because it saves you a lot of time on the tests and a lot of grief if you mess up. Okay? Okay, conrotatory versus disrotatory. If you're doing conrotatory, you're rotating your orbitals in the same direction. Disrotatory, they're rotating in different directions. This changes depending on the pi system you're working with, and if you're in thermal or photochemical conditions. So it depends on if you're doing C2 or mirror, and also if you're opening, closing, things like that. Again, shorthand. Please don't worry about drawing. Like for this example, he's never gonna have you draw in all the orbitals for a 12 pi system. Okay, don't worry about that. Don't spend time on that. Spend time on getting good at this and knowing the basic structure of you have 0 nodes at the bottom, 1 node, 2 nodes, 3 nodes. That actually really helps on questions where he asks you HOMO and LUMO, because you can basically just figure out that this HOMO has 1 node and find the 1 node, and you're good. So stuff like that is really helpful. Stereochemistry. Yeah.
You said you have 1 node. What does that help you with?
So he'll give you identify the HOMO of 1,3-butadiene, for example, and he'll give you 8 options of different orbitals with 4 orbitals in them. You go through and you do process of elimination, find 1 node, and that's your answer. Okay? Things like that. Okay? All right. Like I said, make sure that you don't neglect stereochemistry. That's where I lost all my points on my exams when I took this class. I felt like when I understood the concepts, the tests were really, really easy, but he totally tricked me in stereochemistry. So make sure that you find a system, stick with it, use your hands, draw the molecule flat, bring molecular orbital diagrams, whatever, the little molecule sets or whatever you need. I thought this was kind of funny. Just lighten the mood a little bit. I'm sure not only me has felt this way before, prior to a test. It says, when did you become an expert in stereochemistry? And he says, last night. So, I still don't feel like I'm an expert. So, if you're an expert, kudos. All right, I just want to make sure to reiterate, vitamin D is important. It will be on the exam. Not the whole entire molecule. You're not going to have to reproduce it and try and pick which molecule of vitamin D. But you're going to have to understand that why you even need sunlight to utilize vitamin D in your system, right? You need it to be photochemical, because if it was thermal, then you would have a trans product, and there's a 6-member ring involved, and it's not possible. So you have to get a cis product, and the only way to do a cis product is in a photochemical ring opening, okay? Sigma-tropic rearrangement also occurs with vitamin D, so don't forget that. You rearrange the hydrogen so that you can rotate around a sigma bond in the middle of the ring, so you can make this intermediate. Cold calcium. Yeah?
I remember talking about vitamin D. Can you jog my memory really quick?
Yeah, it's like all over the study guide and on his notes too. So you can go back to chapter 30. Basically what he says is that it's a big molecule, it's like a steroid-looking molecule. And he opens it so that the CH3 and the hydrogen are, yeah, do you remember that? They're facing the same way. CH3 is cis to the other primary. Yeah.
Will we need to know stuff like the 11 cis right now and the other like biological examples?
I'm gonna talk about one more that I like looked through his notes and found the ones that he talked about in his notes, in his study guide and also in class. Cis-retinol does not come up other than the study guide, so I wouldn't really worry about it other than understanding that it's very conjugated. Yeah?
The vitamin D thing was when we was talking about the opening, right?
Mhm.
Like it's just not trans because the rings like prevent it.
Right. Other questions on vitamin D? Again, don't be stressed about trying to reproduce it. Just understand what is happening in that ring. Okay. If you like, what is it called? Reduce the stress to just that ring, you'll be fine. Okay. Cycloadditions. 4 to 2, thermally allowed, photochemically forbidden, like the deals already we talked about. 2 to 2 is photochemically allowed, thermally forbidden. Thymine dimers is an example of this. I thought this was so cool. By raise of hands, who's taken MM Bio 240? Okay, so you guys learned about thymine dimers, right? Totally. And we learned that you have to do like nucleotide excision repair. Like they have to literally cut out a huge chunk of DNA when this occurs. Like it's a big deal. It can block the polymerase. It does a whole lot of issues. So remember that. Make that connection between what you learn and what you are learning here. It will really help you to remember. Yeah, I would just remember this is an example we talked about for 2-2. Again, this is because it's photochemically allowed. So when you're introduced to UV light, then you can create thymine dimers in your DNA. Questions? Okay. This is all due to in-phase overlap as well. That's the only reason why cycloaddition occurs, like we were talking about, is because you can overlap orbitals in phase. All right, sigmotropic rearrangements. I've already told this horror story to my recitation students, but I'll tell it to all of you. Please do not neglect the naming of these. Please, please do not. When I was taking this class, I just kind of skated my way through naming, and I was like, yeah, I mean, it kind of works on the homework most of the time, so I think I'll be fine. And I just told myself that the carbon that it's bonded to before the rearrangement and the carbon it's bonded to after the rearrangement determine the name. That is not how it works, okay? And I missed 10 points. I missed a whole question, 10 points off my grade because I was sloppy with this, okay? Each question is worth 10 points, okay? So do not be sloppy with naming and miss a really easy question, okay? Here is how you name a sigmotropic rearrangement. You find your sigma bond that you're rearranging, and you just draw a line through it, okay? Then you count the atoms involved in the rearrangement on each side of the line you drew. So, for example, if you have let me erase this. If you have this molecule right here, and I have a hydrogen here. And I'm going to do a sigmotropic rearrangement here. And I'm going to move this hydrogen over here. How many are involved on this side? 1. How many are involved on the other side? 3, right? Because I have 1, 2, 3. So this is going to be a 1-3 rearrangement. Okay? No, it's just sloppy for chemists to do, so they just always start with the lowest number. That will totally get you into trouble if you choose the wrong side of the ring. So make sure you're numbering by the atoms that are involved. Okay? That means the atoms that are conjugated to the sigma bond that can move their pi bonds to participate. I could have had this molecule like this, and move to the hydrogen here. And then what would that have changed it to be? A 1,5. Because now I have 3, 4, 5 atoms involved. Does that make sense? Questions? Yeah.
How would we know which one it goes to?
Good question. If it's conjugated, it'll probably go. If it's a hydrogen or a deuterium, it'll go to the end. But questions that he asks on this, he'll give you the starting material and the product, and he'll ask you what's the name. And if it's superficial or interfacial, he'll ask you what the conditions were, which I'll go into in a second. You'll have enough information though to know. Yeah.
So do we need to know like why this is favored to happen or not favored to happen? Like,
I would just, I don't know, I never got asked that on the exam. I mean, you could know that the movement creates some, I don't know. I mean, here it's not really a very good argument, right? Because the double bond's the same substitution either way. That's just a good way that he explained it, but it doesn't always work. He won't ever ask you to know why these happen, they just do.
How would you get like a 3-3? Like how would you?
Good question. So if I'm doing a 3-3, this is my favorite one to draw out actually. I'm going to move this sigma bond here, okay? How many are going to be involved on this side? 3. How many on this side? 3. That's how you make it, okay? Alright, I'm going to move on so I can get, there's not enough time. Here's another one. Don't let this be you when you're doing the naming questions. Please. I've been this. I have been this. Don't let this be you. Is anybody else like really concerned if they've answered like 4 of the same letter in a row? They're like, oh, dang it. Yeah, I get it. Okay, superficial versus interfacial. I'm gonna go really quick through this. I've given a little, like, his little explanation on this slide that you can go over. Basically, if the stereochemistry is not indicated, do not worry about superficial or interfacial. Also, if you're only shifting an H or a D, and the stereochemistry is indicated, H means hydrogen, D means deuterium, which is just a heavy hydrogen, so they basically work the same. If the stereochemistry is indicated, you can do superficial or interfacial determination, no matter how many atoms are involved on the other side. The reason why I said this is because in the book it says you can only do interfacial if it's more than 6 atoms involved. Do you guys remember this? That's if the thing that you're shifting is not hydrogen or deuterium, because there's so much steric strain to shift something that's 6 carbons or less. But he did talk about a specific case where you can do hydrogen or deuterium, and it can be any amount of carbons. It doesn't have to be less than or more than 6, okay? So keep that in mind. That's the only way he would ask you superficial or interfacial on these types of rearrangements, is if it was a hydrogen or deuterium. When determining which one to do, draw the LUMO of the pi system in question. And you do this by doing the number of carbons, that's the number of levels, and you fill in the electrons of the pi system, and then you determine the symmetry of the LUMO and determine the phase of the hydrogen after that. Okay? I know that sounds really quick, but this next slide will help. LUMO will change depending on if you're in the thermal or the photochemical conditions, as we all know. This is an imaginary way to help you get this question right every time. It's not actually how it works. So don't try and like make your mind conceptualize how this slide works. It's just a good mnemonic to figure out where the hydrogen's going to go, okay? Because it really hurts your brain to try and figure out why the hydrogen's coming out of the LUMO. So do not let yourself try and figure that out, okay? All right, also remember 3 to 3 is always superficial, every time. Okay. All right, so this is the thing that he did in class. Again, if it's thermal, you're going to have mirror chemistry on either side. You fill in 4 electrons because there was only 2 pi bonds over here. 2 pi bonds over there. So I'm only using 2 electrons here, but there are 5 carbons involved in the rearrangement, so I'm doing 5 levels, okay? That doesn't really matter as long as you can do pi 2 and pi 3, because you need to figure out the limit. Yeah?
Will photochemical conditions always go interfacial?
Not always, it depends on your pi system. Yeah, it depends on the lumo. Yeah.
You had said the number of like altered pi orbitals depended on the number of pi electrons, but in this case it's different.
Yeah, so this case is different just because it's the device to help you remember. The number of levels is the number of carbons in this case, and then you still fill in the electrons depending on how many electrons are in your pi orbitals. It's just to help you determine the correct limo. Yeah. Okay, I'm gonna move on. Questions? Yeah.
Why did the hydrogen go like wedged on the easy right? And it was dashed on the why did the hydrogen go dashed on the right?
Because it went interfacially here. Because here this is C2. Sorry, it's hard to see, but these are drawn as C2. These are drawn as mirror. Because this LUMO is mirror, this LUMO is C2. And you draw the hydrogen's phase based on where it came out of. It was wedged, which means it came out of the pink part, so it stays pink, which means it has to go underneath. Does that make sense? Here, it was wedged, so it came out of the yellow part, stays yellow, goes to yellow. Okay? If you have any other questions about this, you can come see me after. Okay? Alright, helpful hints for 3-3. I've talked about this in my recitation, but like, please do this every time. It will save your flippin' life. That's all I'm saying. Okay? That's all I'm saying. Okay, here we go. First, you find the 1,5-hexadiene. Second, you break the bond between C3 and C4. Every time, no matter what. Even if it's an oxygen on number 3. You always break the bond between number 3 and number 4. You move it to 1 and 6. Every time. Okay? You move a pi bond between C1 and C2 to C2 and C3, and you move the pi bond between 5 and 6 to 4 and 5.
Will you do that?
What?
An example of that?
I do have something, I think. I have this actually. How about this? Come get me after class. I'll email a picture out to everybody of an example. What? It is! Thank you! Kind soul. Here we go. 1, 2, 3, 4, 5, 6. Move the bond between 3 and 4 to between 1 and 6. Move the pi bond between 5 and 6 to 3 and 4. Pi bond between 4 and 5, and between 2 and 3. That'll work every single time, no matter what, okay? And it'll save you a bunch of time in group home tests. So, this is specific 3 and 3 rearrangement. So we talked about Claisen-Cope and Oxy-Cope. I just applied them to the rules in the slide before. So in the Claisen, your oxygen is number 3. In the 1,5-hexadiene, still same rules. In the Cope, you do just carbon-carbon moving. It's really not too special. In the Oxy-Cope, you have carbon 3 bonded directly to a hydroxyl group, but the same rules apply. And do not forget in the Oxy-Cope to tautomerize. It will happen every single time unless tautomerizing breaks a benzene ring. Then you don't. Yeah?
Sorry. Would that tautomerization of the oxycope be like the only important mechanism to know for these 3? Because he mentioned it quickly in class and then like drew examples of it, but never specifically said, oh, this is an oxycope. So we need to talk about that.
I would know. He talks about them pretty in depth in his study guide, and he did talk about them in class, so I would know like the same arrow pushing applies to any of the free 3s. I would familiarize yourself with the tautomerize mechanism, okay? But again, you don't have to reproduce it, you just have to recognize it, okay? Here's the tautomerization review. Here you go. You can review it when I send these slides out. Okay, here we go. Sorry guys, we might go a little bit longer than an hour, but we'll extend the next review if we need to.
Okay, so we're going to go through chapter 17 fairly quickly because I feel like it's a very intuitive chapter, and so there's not a whole lot of information to talk about in chapter 17, because really the good stuff is obviously in chapter 18. So we're going to go through chapter 17 really quickly. Okay, so aromaticity. Remember these 4 rules. They will save your life. Like, they will help you decide whether or not something's aromatic, non-aromatic, or anti-aromatic. So the first 2, so cyclic, obviously if it's not in a ring, it's not going to be aromatic. If it's conjugated, so that means every single bond, there's a double bond with a single bond in between it, and that goes all the way around the ring. And the entire ring has to be this mixture of double bond, single bond, single bond throughout the ring. And then the really important one is what's known as the Huckel rule, or the 4n+2 rule. And that's really important because if something breaks that rule, then it's known as anti-aromatic and is very reactive. There's also a 4th rule, planar, but honestly, if something's conjugated, it's going to be planar because every single carbon atom, every single atom in that ring will experience some sort of double bond character, making it planar. Okay? So, and molecules are anti-aromatic if they break the 4n+2 rule. So just remember, as you're going through and you're looking at these rings, count the number of double bonds, count the number of atoms, and make sure you can be like, oh yeah, that has an integer of 1 or an integer of 1.5 to help you identify. Okay? When you're comparing rings, so I've never seen Dr. Price's tests. I don't know what he's going to ask, but big thing that can be asked is comparing the acidity of a ring. Remember what he was talking about. Always do the conjugate base. And so when we do the conjugate base of a ring, if the ring's aromatic in the reactants and then has an acid, but then it becomes a conjugate base and it breaks aromaticity in some way, shape, or form, then it's less stable and less basic than a ring that was not aromatic in the reactants, but then as an acid, but was aromatic as a base. Okay? Does that make sense? So always just do the conjugate base, and if something is aromatic, it's definitely a lot more stable than something that's not aromatic. Another thing in reactions. Okay, so if the leaving group leaves, doing a reaction, and the leaving group leaves, and you look at the intermediate, if that intermediate stays aromatic, then the reaction goes faster. If it becomes not aromatic, the reaction goes slower. Okay? Molecular orbitals. This is why Huckel's rule is such a big deal, is because of how the molecular orbitals are done. You know, when we have a conjugated diene, that the molecular orbitals, they follow this row, right? They follow some sort of pattern like this, where they go in increasing order of like energy, right? When we have a ring, our molecular orbitals kind of do a change where we have some number of electrons. So say, let's just do benzene, right? So benzene, probably the most stable aromatic compound we have. And so we have benzene. And so, do you guys remember the Frost circle where he would draw the circle, come around, and then, well, works better if I have it the other way. So basically, so you have a line right there, a line right there, a line right there, a line right there, right? Okay, so that coincides like this, where you end up with a molecule where you end up with a molecular orbital like this. And that's where Huckel's rule becomes important. This shows why aromatic rings are so stable. Because rather than having this very increasingly this pattern of increasing energy, you're gonna have this point where you end up with something like this, and the energy is a lot lower than if it were like this. And that's the important thing with aromatics. That's what makes them such low in energy. And that's something important to remember. So yeah. Also be familiar with lone pairs. So if we have a molecule that looks something like this, so we have a nitrogen, and it's in a 5-membered ring, and we have something along, there's something along these lines. Would you say this, if you can see that right now, this is an aromatic ring because of this electron pair right here that can donate its electrons into the aromatic ring, increasing conjugation. Yeah.
On this one, because it's a double bond, aren't those pi electrons, like that has too many fused atoms?
Sorry. So it'd be something like that. Okay. Good catch. Thank you. So yeah, so like something like this would make it aromatic because these electrons can donate into the pi system. Right? But if we have something, so I'm going to do this real quick. But if we have something like this where if we have something like this, it's already conjugated, and these electrons, they're not a part of the pi system. So make sure that you can look at a molecule. If he gives you a ring, and he goes, which of these are not aromatic, and he could give you a molecule like this, or he could give you an oxygen. He could give you something where instead of a nitrogen, and this double bond right here, it's an oxygen with 2 lone pairs. And you need to be able to decide, like, okay, which of these lone pairs, if any of them, are a part of the ring system and can contribute to the conjugation of the ring. So definitely be familiar with doing things like this. And then yeah, I'm not going to do the practice problems, but you guys can look at them. And then yeah, so there's a little name for you guys. Does anybody have any questions real quick about at least chapter 17? Yeah.
What would the oxygen, if there was no line there, how would a low pair contribute?
If it was a double bond, yeah, so just have something that looks like that.
If it was ever double bond, no low pairs.
Well, because yeah, it only have one lone pair and it wouldn't contribute, yeah.
All right, last section, last chapter. I think we're going to get out pretty close to the time. I asked Dr. Price to give me his notes for chapter 18 because I knew he wasn't going to get to it by today. So I basically just have pictures of his notes on the slides. So I hope that's helpful. But I'm going to send the slides out so you can look at the notes tonight and see what he's going to talk about tomorrow, if that helps with your study. So we're just going to go over them fairly quickly. Question, yeah? Yeah. There cannot be a double bond and 2 lone pairs. Just 1 lone pair if that's the case. Yeah. And there would be a positive charge on it. Alright, also just to catch up anybody coming in, I am recording this review and also sending out the slides and the link to this video. So if for some reason you need to leave, I'm not offended. It's okay. And I will send out the recording of this. Okay, here we go. Chapter 18. So, electrophilic aromatic substitution reactions. There's 2 steps. You have to have a really reactive electrophile reacting with the benzene. The benzene is acting as a nucleophile in this case. And then you need to restore aromaticity. So as long as you understand that basic arrow pushing, you're fine with regards to reaction mechanisms. Okay? Because the arrow pushing is the same for every reaction that we'll go over. In theory, they're all the same. There is a little bit of some different reactions happening to create the extra electrophilic electrophile, but in general, this reaction happening is the same throughout. Yeah?
Did he say in class that we didn't really need to know the...
Yeah, you don't really need to know mechanisms for these right now. I will just understand that the electrons from the benzene ring are going to attack the electrophile. And then some type of base is coming to take a hydrogen off the benzene ring to restore aromaticity. I would just understand those concepts and you'll be okay. Alright, aryl halogenation. This is when you have a halogen compound, usually Br2 or Cl2 is what you'll normally see. It is paired to a Lewis acid, which is iron bound to 3 of its matching group. Does that make sense? So if I'm working with Br2, I need to have FeBr3. I can't have FeCl3, it won't work. Okay? But if I have Cl2, then I need Cl3. Does that make sense? So just make sure to make those matching. The reason why you need this litmus acid is because the bromine compound, the Br2, actually attacks it first and creates a very good leaving group so that you're just left with a Br+. Yeah?
This might be kind of difficult to work, but in the book there were some problems where you had like a long carbon chain coming off like this, and then you had to loop it around and connect it. So that way you have your two cyclohexenes that are connected together. Does that make sense?
Yes. Like you have,
Like you have H2SO4, there's like cyclohexene, then like five carbons, the last one is an alkene, you have H2SO4, and then eventually you have to pull that around and connect it to the cyclohexene. You know what I'm talking about?
yeah.
How do you know if you go like this way or this way on the connection?
Show me after. Because I don't remember a specific question like that. Was it with regards to these?
Yeah, it's essentially the same thing. It's just your extremely like.
Is it at the very end of that carbon chain?
Yeah.
Was it like a chlorine at the very end of the carbon chain?
Well, no, it's not. It's not the chlorine. It's essentially like the double bond. I can show you after.
Yeah. Show me after.
Or the chlorine. You bring it around and connect it. I just want to know which carbon you connect it to.
What I would say is that the carbon directly attached to the benzene ring is an electron donating group, which we'll talk about in a second. If it's an electron donating group, it's going to direct to ortho or para.
I'll show you.
Yeah. Okay. Nitration. This is how nitration works. You have HNO3 and H2SO4. The HNO3 is created into a good nucleophile. You generate, the electrophile. You generate it by the nitro HNO3 group taking a hydrogen off of the H2SO4 group. That OH2 group, as you guys remember from 351, is a very good leaving group. So it will leave by itself and leave you with oh no. Please don't forget oh no. This is like his most favorite thing. Has he talked to you guys about this? Aww. I hope he talks about it tomorrow. Look at him. It's so cute. He wrote oh no and everything. Okay, you make oh no. It's N with two O's. I thought it was pretty cool. Anyway, it's okay if you don't. And then this is just showing that the double bond electrons can attack the nitrogen positively charged either in this conformation or this conformation. It's the exact same. And then you aromatize, same as always. Okay? Good? Questions? Like I said, I'm going to send these out so you can look through them if you want. Here, in order to generate your electrophile, you need to take the SO3, same thing, protonate it. You cause a positive charge on you don't create a good leaving group here, as you can see, but you are creating a positive charge on the sulfur, which makes it an electrophile, okay? Same reaction occurs. Okay. Friedel-Crafts. Oh, this one. So in order to generate, also if you're coming in, if you could just whisper, that would be great. Thanks. For this one, if you have a secondary or tertiary alkyl group, then it attaches to your AlCl3, same type of reaction as the first two. However, it leaves first and creates a carbocation. What do you guys remember about carbocations when they're secondary or tertiary from 351? They can rearrange to more stable carbocations. Do not forget that. He can totally use that on the exam. Okay? Don't forget, if you have a carbocation, that should already signal in your mind, is this going to rearrange to a more stable carbocation in this molecule? If it will, it will. Okay? If it's a primary alkyl group, it's going to stay bound to the AlCl complex. The benzene ring will attack it first, and then the AlCl3 complex will leave. Okay, questions? with 240. You learned about DNA, alkylation, and acetylation, and how they actually will increase the. Anyway, they're really cool. Yeah. He is. Yeah. He's going over this in class tomorrow. I didn't know if people were planning on taking the test tomorrow, so I thought I'd go over it and let you guys see that I have these. And then yeah, we'll go over this tomorrow in class. Same exact reaction as before. AlCl3 is the compound that it attacks, and then if it's a secondary or a primary, it will leave. Or actually, it's just a carbonyl group, so it will leave by itself. Create this triple bonded oxygen. Very strong electron bond. Okay. Electron donating versus electron withdrawing groups. When you have electron donating groups, you have resonance electron donating groups, which is oxygen or nitrogen. And then you have inductive electron donating groups, which is alkyl groups. Because a sp3 carbon is less electronegative than sp2 carbon. Okay? So, remember that. Alkyl groups are inductive electron donating groups. However, resonance electron donating groups are stronger than inductive electron donating groups. Why would that be? Thoughts? Anybody want? Yeah?
Is it because it's like a full charge?
Yeah. Yeah. The electrons are literally moving into the ring with resonance. Whereas inductive, it's just the electrons are feeling a pull from the ring. So their presence will be a little bit more in the ring. They won't actually move there. Does that make sense? So that's why resonance electron donating groups are stronger. If you have two electron donating groups on a benzene, and you have to pick which ortho and para you're going to choose, the one that is a stronger electron donating group, the resonance one, will be the one that directs the substituents that get added. Okay? Electron withdrawing groups, they decrease the electron density within the ring, so they decrease the reactivity of the ring, which basically also means decreases its basicity, decreases its nucleophilicity, things like that. Same thing with electron donating groups increase electron density, so they increase reactivity, which is why there was a question on the practice exam that asked increasing which one's more acidic, and it had 3 different benzene rings. Do you guys remember this? Okay, and the one that had the electron withdrawing group was the more acidic one. And that's because it had less electron density within its ring, which means it was less basic. And if something's a weaker base, what is it? Stronger acid, okay? So if it is a less reactive molecule, it's more acidic. Does that make sense? It's good to make that connection in your mind, and you can reason through it. If you have a weaker base, which means you have less electron density within your ring, it's less of a nucleophile, then it's going to be a stronger acid. Okay. Regioselectivity, resonance, and inductive EDGs will do ortho and para. Remember halides, they actually can do resonance within the ring, but their inductive effect is stronger, so they're actually withdrawing groups, but they still direct to ortho and para. So don't get that mixed up. And then resonance electron withdrawing groups are always meta. Yeah?
Can you maybe draw that out? Why that halide or electron withdrawing group? Because it doesn't make a lot of sense.
So I can just talk about it. I can also draw it out if you want. But basically, a fluorine is more electronegative than oxygen and nitrogen, and it's one of the halides. So since it's the most electronegative that you can possibly get within the periodic table, it's right up there, most electronegative one, it is going to induce the electrons towards it and act as a withdrawing group way more than it will donate its electrons into the ring. Chlorine and bromine do the same thing. Okay, other questions? He may not talk about this in class tomorrow. If he doesn't, you don't need to worry about it. But I just wanted to make you guys aware there is a thing that he talks about in his study guide for like 5 pages. It's called MAVI, and it's something he loves a lot. If he talks about it, I would remember what he talks about in class. Okay? Other than that, you're good to go. And if you came here for the 7 o'clock one, then feel free to stay. Yeah.
Can you give an example of the last one you mentioned?
Say that again.
Resonance of electron bonds. That's metal. Can you like give an example?
Yeah. If you didn't talk about it in class,
It's like on the like there's this column where you have to use like MCDPA to get like a box site.
technical cells are different kind of tests. As long as
So like just go look.
That is the oxygen coming out in the middle one.
Resonance, this can come in here, and then this comes out here, and then
You basically put the positive charge on
oh yeah.
What would be like a resonant electron?
A resonance electron would be like have nothing O.
Oh, because that charge can come from that. Okay. Gotcha.
I'm actually not. Hey, if you're here for the 7 o'clock, I promise we're getting started really soon. We just ended the 6 o'clock one, so we might go like 10 minutes over if that's okay. If you need to leave, that's fine. I'm actually recording the review, so you guys can leave whenever you need to and not send the link out. So.
That was it.
So this one, he makes a specific statement instead of it that says whenever any atom is bonded to the benzene ring and to something that's more electronegative than it, it is an atom. Okay, yeah, it's just in the book. It's in his study group. Electron withdrawal.
What makes all that really good?
Gone to 5.
It's technically bound to
Well, it's got lone pairs in
That's fine. Combine down. Sorry. Yeah. Oh, you're right. One pair should have it. But in the case it still would be an electron charge. Yeah. Okay.
This is what I was talking about. How do you know if it bonds to there or there? Oh, it's the resonance.
Hey, Ty. Good work.
What did she just say?
Yeah, what's up? This one? That one? With yeah. So the halides do something really weird that even though they're so electronegative that they'll pull electrons away from them. Okay. So yeah. Yeah, so basically the idea, and I'm just going to quickly draw. So when, because I'll quickly draw and then we'll get started, okay? So when you, so say you have, we've already gone through the first reaction where we put a halide on there. And so we have something like that. And so the reason that the halides, even though they're electron withdrawing, even though they go ortho or para, is so say we put some molecule right here, which then gives us a carbocation here. I'm not going to go through all the resonance, we're only going to do it real quick. But when we go through these resonance structures, we ended up with something that looks like this, with X, and then I can't remember how the double bonds go. Basically, we end up with a carbocation right here. But normally that wouldn't work because we'd have this positive charge right here. And you don't want the positive charges so close together. But the thing that the halides do that other electron withdrawing groups don't do is because they don't have that positive charge, they can actually donate a pair of electrons and form a double bond. They don't want to do that, but they can if they have to. So that's why even though they're electron withdrawing, they still technically donate into the pi system. They help stabilize that positive charge and make the molecule more stable. Okay. All right. So for those of you that have come for the 7 o'clock time, we're gonna get started.
Here, I'll start from the beginning so I don't have to see all our sequence. Just kidding. Go quick, go quick.
Welcome, everyone.
Yeah. Okay. So for those of you that came at 7 for the 7 o'clock meeting, don't worry that you feel like you missed anything. Everything we taught from 6 to 7, we're gonna teach again. So for those of you who are staying from the previous hour, just be prepared. You're going to get the same information. So we're recording this, so don't feel like you can't leave or you're going to miss information. We're recording this, and then we're also going to post our slides. And then if you have any questions, always feel free to ask. If something doesn't make sense, don't be afraid to raise your hand. So we're going to just go chapter by chapter. We don't have a lot of practice problems. We don't have, we're mostly going to just hit the concepts, because if you guys understand the concepts, you'll be able to do any problem that you see on the test. Okay, so the first thing we're going to talk about is conjugation. Remember, conjugation is a continuous ray of p orbitals through a molecule. So if you look up here, this molecule right here is conjugated because we have a pi system, another pi system, but then this double bond, and through resonance we can connect that. And so that's how we know this is conjugated. While something like this is not conjugated because of this sp3 carbon right here. And same thing right here. We have these two sp3 carbons that can contribute to the conjugated system. One thing to remember with conjugation is that it's a lot more stable than just a regular molecule. This will be a lot more stable than either of these two. And that's due to pi orbital overlap and then just delocalization of the electrons. Okay? And just remember, he talked about this on his practice exam, but sigma bonds in a conjugated system are shorter than regular sigma bonds, but they're not as short as double bonds. But that's because in a conjugated system, because of that delocalization and because of resonance, these bonds can exhibit double bond character. Okay? Any questions? It's really easy stuff, like chapter 16 isn't too bad. Yeah, what's up?
Why would they be the same length as the one?
Because they're still a single bond, but it's because of resonance. And so, I don't remember if Dr. Price went over this, but when a molecule goes through resonance, this isn't like what that actual molecule looks like, but because of resonance, it's actually like an in-between of molecules, right? And so that's why, this, even though this doesn't have a double bond, it technically is experiencing some double bond.
So if it technically is experiencing a double bond, right, it's not just like a representation of it.
Right.
Then wouldn't it be the same length as the other double bonds because it technically is a double bond?
Right. But that's where the resonance comes in, because at some points it can be a double bond, some points it's not. Okay. So that's why it's in between. Yeah.
Just along with that, the reason is it's also sp2. And since it's an sp2 carbon, it's going to
Thank you. Okay, so now we're going to move on to pi orbitals. And so remember, in a conjugated system, the number of pi orbitals you have. Yeah, what's your question?
Sorry, just really quick. Would all of the bonds be equal in that system because they're all partial bond characters, or?
Right here.
Yeah.
Yes and no. Yes, because at one point they will be single bonds, and at one point they will be. But then no, because at another point they'll be double bonds. So that's why they're. So yeah, you're. So they're all the same length, but they're not exactly single bond length, but they're not exactly double bond.
But each carbon, like C1, C2, C2,
Yeah. 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 Okay. Any other questions about conjugation? Okay. So pi orbitals. So just remember that the number of pi electrons you have coincides with the number of pi orbitals you should have. And then just remember that as we go up in energy, then we get more nodes with our system, and that we'll always have a homo LUMO. And you always feel electrons starting with the lowest energy and going up. Another thing to remember is pi orbitals. This molecular orbital system is very important with conjugation, and in the sense with visible light. So as a molecule gets more conjugated, its energy, its homo-LUMO gap right here. So here's the LUMO, here's the homo. As a molecule gets more conjugated and bigger, those homo-LUMO gaps will get smaller and smaller, which will allow it to get closer to visible light. And so we'll show you a molecule that's very conjugated. Excuse me, it has like 12 pi electrons. And you'll see that molecule falls within the purple light range, I believe. Okay, is there any questions about pi orbitals or what we're going to do with them? And it's important, another thing important is that with the homo-LUMO, it's important to remember that these things, the homo is what can attack in a reaction, and the LUMO is what gets attacked. Okay? And we'll talk about more of that when we get to Diels-Alder, like right now. So Diels-Alder, remember, Diels-Alder is a cycloaddition, just like what we talked about in chapter 30. It's a 4 plus 2. With Diels-Alder, there's a set of 4 rules that we'll talk about. But just remember, thermal is always going to be a 4 plus 2 addition. Photochemical can never be a 4 plus 2. And Diels-Alder is always going to follow 4 plus, is always going to go be a 4 plus 2. So always be a thermal. Another thing is, Dr. Price, I don't know how he's going to write his test, but he might show you a molecule like this that's trans. And you have to make sure that before you do the Diels-Alder reaction, make sure you convert it. Because he might ask you, oh, what is the product, or what do the reactants look like? And so he may show you a Diels-Alder product, and then say, what are the reactants? And he could give you one of these as an option, and that won't be correct. And the reason it's not correct, and the reason we can't have a diene that's trans, and we need a diene that's cis, is that when we bring these molecules together, if it's trans, we're not going to be able to, the dienophile is not going to be able to reach. So if the dienophile is coming in from this side, it can reach this double bond, but it can't reach this double bond, which is why we need to bring it to cis. Okay? And so here are the rules. So with Diels-Alder reactions, these are the full rules that we have to follow. It has to be a thermal reaction. You have to form a 6-membered ring. You're going to be breaking 3 pi bonds. So with this, let me see if I can bring it down. So with this, we have, this can count as our diene, and then this will be our dienophile. So in the Diels-Alder reaction, in our reactants, we have 3 separate pi bonds. We're going to break all 3. Yeah, I'll get to you in a second, Mark. We're going to break all 3, and then we'll form 2 sigma bonds and 1 new pi bond. Yeah, what's your question, Mark?
Could you remind me again, maybe I just forgot, a concerted reaction? What's that mean?
It just happens in one step. So part 4 is a concerted reaction, meaning we're not forming a carbocation, meaning there's going to be no hydride shifts or things like that. And so to kind of show you, so if we rearrange this, I'm just going to write R for rearrange, but we'll have something like that. And then concerted reaction is everything happens in one step. Okay? That's all a conserved reaction means, is everything happens like right there. And so those are the 4 rules. Does anybody have any questions about the rules or Diels-Alder in general? Yeah.
So, questions 4, 5, and 6 and 9 is exactly like all about creating the products of the reaction.
Right.
I don't know, some people have a hard time seeing like if there are constituents on either one, either the file or the how to predict stereochemistry.
Perfect. You're leading us into our next topic. So stereospecificity. So to answer his question, some important things with Diels-Alder is first stereospecificity. So whether it's an enantiomer, diastereomers, whatever, right? And then there's regioselectivity. So stereospecificity. So say I have. So come with this molecule. And this is important. I'm talking stereoselectivity. Sarai mentioned earlier in our previous review that when she took this class, the stereospecificity is what killed her with Diels-Alder, and she'll talk about it when she talks. But so to kind of go along, so if we say we have something like this and we have a substituent like that, right? And then a substituent like that, and then we're going to react it with just a regular ethene. One trick I've learned doing Diels-Alder is that your inside substituents, right here and right here, and your outside substituents should match. So if you're looking at this is trans, and then this is also trans. So what we're going to have is these two are going to be the same. They're going to be cis to each other, so they're going to go in the same direction whether up or down. And then these two will go the same direction. Does that make sense? Okay. And so, and like even with this, so let's say if we have something that's cis, these two are always going to be cis, whether it's dashed or wedged. Okay. Does that make sense? So yeah, so the product of this okay, right, so I'm going to number the carbons real quick so you guys can see 2, 3, 4, and then I'm just going to say 5, 6, okay? So this is 1, 2, 3, 4, 5, 6, and so right here, since these are cis, I'm going to draw these as wedges, and then I'm going to move this one right over here. Okay, so these two have to be the same stereochemistry. It doesn't matter whether it comes on top or bottom, right? We just have to make sure that this outside and this outside are the same stereochemistry. So I'm going to make this one down, H, and then just different, like that. Does that make sense?
Yeah.
Okay.
So, in what cases are there going to be like enantiomers as well?
So something like this will also have an enantiomer because we can just rotate that, right? We can just flip it over, and then this will be up, and this methyl group will be down, and then the H's will be flipped. And so this will be an enantiomer, so this will have. But then there'll be cases where it's just a meso compound, and it doesn't matter which way you flip it. So if we have something like this, like if we just have this product, and we don't have these, and it's just that. Because if we flipped it, it's just the same problem, same thing. So that's kind of, it's just looking at what your substituents are and what they get you. Yeah.
So in addition to the enantiomer that you would have for that one, would you also have one where the two cis compounds are dashes?
Mm-hmm.
And then, so there would be two sets of receivers.
Yeah.
So the dienophile or the 5 and 6, if it was trans, you're saying it would also still end up being cis on that side?
No. So if it's trans, then in one of them, that's going to be trans, yeah. So you just have to make sure, like, whatever, whether it's cis, trans, in my products, I get the same setup in my reactant. or in my reactants, whatever's in my reactants, I get the same set of products. Yeah.
So essentially, every time you get it like that, if you draw your plus and minus, you're indicating that there's an enantiomer.
Yeah.
When do you have to also account for a diaster?
So with this, I didn't draw the diastereomers, but you'd also have to account, because you can flip these, and then you can have dashes, and then you'd have to change these. So then you'd have a second set of a diastereomer with this, plus it's also following an enantiomer. Yeah. Yeah.
So anytime you're doing this when you're determining stereochemistry, you have to imagine that this is my diene and this is my dienophile. It could react like this on either side, right? Top or bottom, technically. But this could also be flipped like this. Let's say my substitution was right here. This could be flipped like this, and it could also react top and bottom. Okay? So the top and bottom is the enantiomer part. The flipping is the diastereomer part. Okay? And then once you draw all of those products, then I would look at them all and say, are any of them the same? And then if they are, then you want to draw those. Does that make sense? You're always going to have enantiomers for these. There's no enantiomeric specificity. But you could have diastereomers depending on which one. Okay? But there's sometimes where the olefin is such that no matter where you flip, you're going to make the same molecule no matter what. So then you don't make diastereomers. Okay?
Could you give an example of what diastereomers would look like?
It's just that they stay the same.
Oh, right.
Like they stay trans, but then those
Right.
numbers go cis.
Right.
Dash.
Yeah. So it'd be like, so we have this molecule, right? And we have our two dashes with our H, and then our methyl group with our dashed H, and then these would be like that, right? And then we have this. And really, it's just drawing the same molecule, but these are going to be dashed instead. These two cis products, right? Are going to be dashed. Does that make sense?
Could you redraw it?
Yeah. That's it. And then you just flip it and you get its yeah. The methyl groups? Oh, sorry. So in my earlier problem, I had something like this. So I just erased. Let me show the front one. Okay, we're gonna get going. Remember, you don't need an endo or exo with Diels-Alder, so that's something nice you guys don't have to worry about. And then I have a few practice problems, but I'm not gonna go over them. You guys can look at them, okay? Or if you have questions about them, you can look at them and come talk to either Sarai or me. But here's a cute little meme for you guys to show, like, this is what Diels-Alder kind of does if you were to see it happen in real life. It's kind of mosh pit, but yeah.
Okay. How are we doing? Questions? Stereochemistry? Again, please do not neglect stereochemistry. We have a funny meme regarding that later. Yes?
If we're not feeling great about stereochemistry yet, what's a good thing to do?
I think at this point, you should go through, have you done the practice exam yet? I would do the practice exam, and then I would look through his key, and I would teach yourself all the things that you were missing with stereochemistry. Because the first half of it is Diels-Alder, basically, right? And so you can go through and see, okay, what principle did I not understand that made me miss some of these, or that made me make some that weren't actually there. Okay. All right. Here we go. Chapter 30. All right. Also, I just have a lot of words on my slides because I get caught off on tangents a lot. So, okay. So, ring opening. Anytime you do ring opening, you need to take the electrons in the sigma bond and empty them into the pi system, the LUMO of the pi system, of the closed ring. Okay? So the ring is closed. Let's say it has 2 pi bonds, which means they have 4 pi electrons. You're going to figure out the LUMO from there and then put the sigma bonds into that LUMO. Okay, questions on that? Okay, and then remember that when you open the ring, you're going to have a different pi system than the pi system you started with. So I have some people who have asked me if, like, there's been confusion because you have to move pi bonds when you open and close rings, right? But the carbons that you're moving them to are out of phase in the LUMO that you start with on the closed ring. And so a lot of people have been like, well, but they're out of phase, so they can't have pi bonds there, right? Well, they can't in that pi system, but you're making a new pi system for which they will be in phase, and you can do pi bonds there, okay? So don't get tripped up with that. Ring closing, you're using the HOMO of the pi system to open the ring, okay? HOMO of the pi system, or I mean to close the ring. Yeah, sorry. Yeah, use the HOMO of the pi system of the open ring to close the ring. Okay? Something that helps me in my experience with these tests is being able to do shorthand for orbitals. So you don't have to draw all the orbitals, you don't even have to draw them all on your molecule when you're doing opening and closing. You just need to know what the symmetry of the very outside orbitals are. So I always, let's say I have a 6 pi system, so I have 6 pi electrons. I'm going to draw 6 levels, mirror, C2, mirror, C2, mirror, C2, fill my electrons in. Whenever I have any of these questions, this is my very first thing I did on the side, every time. And then from there, I looked at the question, I said, okay, I'm being asked to open the ring. So I'm going to look at the LUMO, which is C2, so I know that they're going to be opposite in phase on the ends. And then those are the ones that I'm going to close with or open with. Okay?
Can you briefly review between C2 and mirror symmetry?
Yeah. So C2 on the outside looks like this. Where if you like took this and rotated it 180 degrees, it'd do the same thing. And then mirror. What's in it?
Could you explain why when you're opening the ring it's using the LUMO and when you're closing
Yeah. So when you're opening the ring, you're taking the sigma electrons from the sigma bond, and you have to put them somewhere. So you need to put them to the most available empty orbital, which is going to be your LUMO. And when you do that, you create new pi bonds. Okay? And then you have to move pi bonds to accommodate for that. When you're closing the ring, you have to take electrons from the HOMO and put them into the sigma bond. So you take the HOMO, rotate them into the sigma bond, and create the sigma bond. Okay? Yeah?
So for ring opening or for ring closing, you just draw like what you have up on the board.
Mhm.
It doesn't matter. So I remember one time in class you talked about like you have a sigma and then you have a pi star, and a sigma star. You like drew that for ring opening.
That's a way that you can look at it. I don't like to look at it that way
So I
because
can
it
just stick to
confuses me.
that?
Oh yeah, I stick to this all the time. It always rings true. You can do the sigma star pi thing if you want. I know some people who do that and it works well. So whatever works for you, do it. Okay, conrotatory versus disrotatory. If you are rotating the same direction, clockwise, it's going to be counterclockwise. If they're both rotating the same direction, it's going to be conrotatory. If they're rotating in opposite directions, disrotatory. This changes depending on the pi system in question and if you're thermal or photochemical. So, for example, the 4 pi system has a C2 HOMO, whereas the 6 pi system has a mirror HOMO. Okay? So make sure you can do things like this to keep yourself on track. Shorthand. Oh, also, knowing orbitals, you won't have to like reproduce the entire orbital diagram here.
But you need to understand the basic concepts so that if he asks you, here's this conjugated pi molecule, what is the HOMO of it? And he'll give you 6 or 8 options of different pi orbitals. And you'd have to pick which ones they were, or which one was the HOMO. So a good thing to help you to make that question quicker, if he asks it, is you can also think of the fact that you're going to start with 0 nodes, then 1 node, 2, 3, 4, 5. So you're going to increase nodes every level. You can look through the different options that he gives you and find the one that has, in this example, it's 2 nodes. So that's option. So it's understanding the different concepts of the orbitals that will help you answer questions like that. Okay? But don't feel like you have to, do not waste time drawing out the orbitals every single time. They're really only pertinent for questions like that. What's the HOMO? What does a LUMO look like? Other than that, you just need to know what the symmetry on the ends look like. Okay? Stereochemistry. Find a system that works for you and stick with it. Use your hands, draw the molecule flat, whatever works, but please do not think that you can just go into the test and you'll see it. Okay? You have to understand it. Like Tyler said, I lost a lot of points on my stereochemistry in this class. Because he doesn't give you just A through D. He gives you A through F or A through J. So it's really easy to trick you in stereochemistry. So make sure that you're understanding what's going on.
Can you give us an example of that? Like a way he would trick us?
He could trick you with sticks. Totally trick me with sticks. Where you think you have a racemic mixture, but they're trans, and then he gives them to you for example, if you have a molecule like this is very simple, but it drives my point home. In your mind, you think, oh, well, I can just draw these as sticks, because there's a racemic mixture. But if you draw them as sticks, it's also indicating that they could at some point be like this, which is not the molecule. And then you get it wrong. So stuff like that. You'll see sticks a lot. At least I remember seeing them a lot. Okay. Here's just a little funny meme that just describes my life in organic chemistry. So if you relate, then it's okay. It's okay if you don't, it's fine. But anyway. Okay, vitamin D. I just want to talk about this really quick. He talked about it extensively in his study guide and also extensively in class, so I wanted to go over it because it will most likely be on the exam. Why does this process have to be done in photochemical conditions? The answer is right here, but anybody want to explain it? Okay, I will do it. So if you do thermal disrotatory rotation, you cause a trans double bond within a 6-membered ring, which is too much ring strain, it's impossible. So you can only do photochemical conrotatory rotation because it creates the cis conformation of the double bond that is also attached to the 6-membered ring. Okay? So that's why you need sunlight in order to utilize your vitamin D in your system, is because you need it to be photochemical ring opening in order to make the intermediates for using vitamin D. Okay. There's also a sigmatropic rearrangement. I don't know how much detail you need to know about that, other than the fact that it happens so that you can rotate around a carbon bond in the middle of the ring to create this intermediate. So I just remember that it's doing photochemical ring opening as well as a sigmatropic rearrangement.
Do you know if it's like a 3-3 or a...
It's a 1-7. He talks about it in his notes. Okay, cycle additions, we talked about 2. There's a few other ones that he had you do in the book, but these are the ones he talked about in his notes and also in lecture. So, in his study guide and also in lecture. So these would be the ones I would focus on. 4 to 2 is thermally allowed but photochemically forbidden, like the Diels-Alder, and then 2 to 2 is photochemically allowed and thermally forbidden. And an example of this is thymine dimers.
Who has taken M Bio 240? Raise your hands. Okay, so you remember learning about thymine dimers. This is why they happen. This is why UV light is bad for your skin. This is why it damages your DNA. And this is like huge stuff. Like if you do like nucleotide excision repair, you have to cut out like a whole section of your DNA to fix this stuff. So it's pretty big. It's important to know. Also, this is all due to in-phase overlap. And I would make sure to understand the stereochemistry of these reactions just the same as it deals with water. Alright, sigmatropic rearrangements. I wanted to go over the naming because I missed a question when I took this class on naming because I was lazy. Okay? I was a lazy namer, I didn't learn how to do it this way, and I learned it wrong. Okay? So don't learn it wrong, don't be like me. How I did it was I just skated through saying, well, whatever the sigma bond was, whatever carbon the sigma bond was bonded to, and then the sigma bond it ended up being bonded to, that's the name. That sometimes works, but it does not always work because it's wrong. Okay, so if you're doing it that way, stop. Okay, because you'll get a question wrong and it's 10 points. Yeah.
Can you give us a unique example of rearrangement question? Like one that we didn't do last time?
Sure. After I go over this.
That's fine.
Okay. So, actually, I'll do it while I do this. How does that work? Okay. Let's say I have a molecule. I'm trying to think of a unique example. Let's see. Okay. So this is how you name. Listen up. When you name, you cut the sigma bond that you're rearranging in half. Okay? Just draw a line straight through it. Then you need to consider the molecules that are involved in the rearrangement. It's not the molecules of your whole, like it's not the atoms in your whole molecule. Do not number your whole molecule. You number the molecules that are involved, okay? So on this side, how many molecules are involved? 1. If it's 1, you start with the number 1, okay? On this side, how many? 1, 2, 3, 4. Not this way. This way, 5, 6, 7.
You count to the end of the conjugated pi system.
Yeah. If I numbered it this way, 5, 6, I guess it'd still be 7. So this is a way in which you can get this wrong. But there's some times where you number the wrong way around the ring, you can get the number. He goes over one in class. Okay? And then how I would rearrange this is I would take this off, move all my double bonds over. Okay? So that's how you name every time. Yeah?
Was that after you're in the end of the conjugated pi system?
Yes.
So you can't stop at like 5?
Yeah, it'll go all the way through.
Do we have to be able to predict where the rearrangement's going to be?
He usually gives you enough information where it's not ambiguous. Like he'll say do a 1,7, or he'll show you a 1,7 and say, tell me the name of it. So he won't give you like just a reactant and say, show me what it is and also the name. Yeah, usually gives you enough. Okay. Oh, I clicked the. Okay, my religion teacher did this like. Yeah.
Just to review, when does the rule, like 3 or 4 rules apply where you have to always look for the one?
I'm gonna go over it. That's for 3-3.
That's 3.
Mm-hmm. This is another funny meme. I don't know. Have any of you like been to multiple choice tests and you've answered like 4 in a row that are the same letter and you like freak out in your heart because you're like, I'm probably answering these wrong. It's kind of the same thing. Okay. here we go. Superfacial versus interfacial. This one. Who wants me to go over it? Raise your hand. Do you guys understand what's okay? I'll go over it. Okay, so the stereochemistry, if it's not indicated, you don't have to worry about this. Just like let it leave your mind if he doesn't give you stereochemistry. If he's giving you stereochemistry on an H or a D and that's the one that's shifting, that is when you need to do superfacial versus interfacial. You can do this determination with a hydrogen or a deuterium, no matter how many molecules are involved on the other side. There was a discrepancy in the book where a lot of people were confused because it said you could not do interfacial unless you had more than 6 atoms on the other side. That's only if it's something other than hydrogen. So like a 3-3 rearrangement, for example, only goes superfacially. But if it's a hydrogen or a deuterium, then you can do a superfacial versus interfacial, which was what he was doing here in class, which I'll go over in a second. So, when you're determining which one to do, you draw the LUMO of the pi system in question, which is a little bit different than how you normally do it. The levels is the number of carbons, and then the electrons is the number of electrons in the pi system. And then you determine the symmetry of the LUMO, and then determine the phase of the hydrogen off of that, which I'll show you in a second. The LUMO will change if you're in thermal or photochemical, like always. And this is just an imaginary way to help you get the question right every time. It's not actually how it works. A lot of people have been trying to figure out like how this actually works with this explanation. It's not going to work because you have to like use the LUMO to determine the phase of your hydrogen, and the hydrogen's not leaving from the LUMO, okay? So, but it is in this case to help you get the question right. Does that make sense? Hopefully it will when we show you this. Okay, so here he indicated the stereochemistry of the hydrogen, and he did it superficially for thermal. He could just give you this part and say what's the product, and you'd have to show the superficial part. Yeah? This is where it gets a little bit different. You technically don't even have to worry about it, and you'll still get this right, because you really are only looking at the LUMO, which is pi 3. Does that make sense? So you don't even have to draw pi 5 and you'll still be okay, but I'll explain it really quick. It's the number of carbons that are involved. And that's all I'll say. I won't try to confuse you anymore. With this mnemonic device, if you're using this to determine superfacial versus interfacial, do the levels determined by how many carbons are involved. Okay? And the electrons are how many electrons are in that pi system between those carbons. Okay? Then this one was mirror. So you draw the LUMO mirror, and then the H was a wedge, so it came out of the yellow part, so it stays yellow, goes back to yellow. Superfacial. Yes?
I have like 2 questions, one inside the other. One is how to determine the phase of hydrogen, and then based off of that, how does the phase of hydrogen relate to the LUMO? Could you say it one more time?
Yeah. So it's not because the hydrogen is leaving from the LUMO. This is just an easy way to get this question right, okay? I can't reiterate that enough, okay? The hydrogen is not coming out of the LUMO, okay? But it's just an easy way to determine if it's interfacial or superfacial, okay? I draw my LUMO, which is, oh, I hate doing that. Can you see? Okay, my LUMO's up there. It is mirror. Let's do, I'm looking at the top right, okay? My hydrogen was a wedge, which means it was on top of my LUMO, which means it's coming out of the yellow part. Do you see that? If it's coming out of the yellow part, it's going to stay yellow. And then it will go back to yellow, which is why it was superfacial there. Whereas here, this is C2, this LUMO here. So my hydrogen's coming out of the top, which is the pink part, staying pink, going back to pink, has to go underneath interfacial. Okay? So again, this is just a good way to do it, just like an easy, quick way. If this doesn't make sense and you figured out a different way that would make sense to you, then totally do that. I just wanted to go over it in case. Yeah.
Sorry, why is the pi 2 mirror? I thought you started mirror, and so
The pi 3 is here.
Oh,
Which is a little bit.
okay.
Okay. Here's my helpful hints for 3-3. If you're in my recitations, you've already seen this. If not, you're welcome. This will work every time. No matter what 3-3 you're doing, it will always work. You find your 1,5-hexadiene. I'll do a pretty easy example here. Okay, this is a 3-3. It's a cope. It's pretty easy. 1, 2, 3, 4, 5, 6. That is a 1,5-hexadiene. Okay? Next thing, I need to break the bond between 3 and 4. Okay? I'm going to reform that bond between 1 and 6. I can't have carbon bonded to 5 things, which means I need to move these double bonds over between 3 and 2 and 4 and 5. Okay? That will work every time. If it's a Claisen, a cope, an oxycope, I have a slide right here that explains how these apply to these rules. It will work every single time. So I would get comfortable with those. The Claisen, oh, that's cool. The Claisen is a C to O sigma bond that you're moving to be a CC sigma bond, and a C double bond O is formed. That's because the O is the number 3 of your 1,5-hexadiene. Okay? Same rules apply as before. Cope, it's pretty easy. It's what we just did right here. Carbon-carbon to a carbon-carbon. Nothing special. Oxycope, same thing. Carbon-carbon to a carbon-carbon, but on C3 it's also bonded to an OH group. And same rules apply, but you cannot forget to tautomerize. Don't forget that. Here's how it's tautomerize if you forgot. Yes? An oxycope would be where an oxygen's right here. And here, this is an enol group. And if you remember from Michaelis, and I'm pretty sure Castle did this too, anytime you have an enol group, it's going to tautomerize to the fermion, which is this. Is if the OH group is bound to number 3 or number 4. It doesn't matter which way you number. The only time when this doesn't happen, when it's an enol group, is if this OH group is bonded to a benzene ring, and you'd be breaking a benzene ring to tautomerize, and you don't. You just leave it as an OH group. Otherwise, you tautomerize every time. After you do the rearrangement. Because when you rearrange, you're going to create this. So this rearrangement has already occurred. You have an enol left, you tautomerize it so that it looks like that at the end. Okay? So he'll give you the enol form, and it will not be the right one as an option. It will be the tautomerized one, and you'll have to know that it's the tautomerized one.
But you can still do the whole, like, traveling through.
Yeah. You can still do the whole rearrangement and then tautomerize to the very end of the email. Is that what you're asking?
I meant like the, like, 2 sides of one.
Oh yeah, when you're doing the naming. Is that what you're asking?
No.
Like,
That.
yeah,
Like,
this.
still orthogonal process.
Yes, this will be the exact same. You'll just end up with this, and then you'll tautomerize this to this. Okay? Okay, there we go. We have 2 more chapters, but this one's going to go quick, and then we'll do mine quick. Okay? So hang in there.
Okay, so yeah, chapter 17 is really easy. Not a whole lot going on with chapter 17, right? Chapter 18 is really where the good stuff happens. So, big thing about chapter 17 is just really defining what aromaticity is. And so here are the 3 rules, requirements, whatever you want to call them. These 3 have to be true in order for something to be considered aromatic. So the first thing is cyclic. So if you see something like this, it's not aromatic because we have to make sure that there's the sigma bonds connecting this to make it a ring. Second thing is it's conjugated. Like right here, if there was a bond right here making this ring, well, yes, it's cyclic, we still have this lack of conjugation right here. So no, that would mean this molecule is not aromatic. And then the last rule is Huckel's rule, which is just the number of pi electrons inside of our ring ends up to having an n equals some integer, like 1, 2, 3, or whatever. And something I like to do when I'm trying to decide if it follows Huckel's rule is I like to just set it equal to however many n solve for n. Like some people prefer to just look at it and be like, oh, it has 6, or it has 12, or 10, or 14. And be like, oh yeah, it completes Huckel's rule. I personally like to just go ahead and solve for n, but that's a preference of mine. Technically, there is a fourth rule, that planar, but most likely if something is if something's conjugated, it's going to be planar because all the bonds have an sp2 hybridization character. If things, yeah.
This might be an extreme example, but could there be instances where there is a aromatic compound that only has 2, like a cyclopropane or something like that?
Cyclopropane. So like something like this.
With a double bond.
With a double bond. Yeah, so if we have that, then yeah, that could be it. But that's very rare. So the other thing, just remember that if it breaks Huckel's rule, if you end up getting some n, if n equals 1.5 or 0.5, or anything that's not a whole integer, then it's anti-aromatic instead of non-aromatic. So just keep that in mind as you're going through these. When you're comparing rings, so Dr. Price talked about in lecture, if we're trying to compare the acidity of 2 rings we could consider aromatic, always go to the conjugate base. And if you go to the conjugate base and it ends up making it not aromatic versus the conjugate base of something else keeps it aromatic or makes it aromatic, obviously the one that's not aromatic is less stable than the one that is aromatic. And same thing with reaction. If you're going through a reaction, the leading group leaves and it makes it aromatic or it makes it not aromatic, obviously the aromatic is going to make it faster than the not aromatic. Okay? And then molecular orbitals and aromatic rings. This is why Huckel's rule is so important, right? Because when we're dealing with just with regular conjugated molecules, something like this, right? Our orbitals always go in this upwards pattern of increasing energy. But when we have a ring, so let's do a 5-membered ring, and I prefer to draw it with the point down. And when you do a 5-membered ring that's aromatic, okay, then you can do something like this. You can do something like this that shows it's an aromatic. Okay? And so this is why Huckel's rule is so important, that when we're drawing these orbitals, instead of drawing them in this in this ever-increasing order as energy goes up, like this is energy, we can actually draw like this, where we have a molecule where the molecular orbitals are actually in the same energy level. And this greatly lowers the energy, this greatly lowers the reactivity of these aromatic rings, which makes them more stable than, say, dienes, and definitely more stable than anything that's not conjugated. Okay, is there any questions about that? And this is kind of the idea of when Professor or Dr. Price drew frost circles. So you know to draw the circles and you draw the lines, right? That's one way to think of it. Yeah.
Do we need to understand why some orbitals are the same energy, or just know that that's how it happens?
I'd say just know how that's why it happens. I don't think he's going to go that deep into understanding why. Going along with these, it's also important to remember what contributes into the pi system. So there are several examples that we can show you. I'm going to draw 3 specific examples real quick so you guys can see. Okay, so there's something like this. I did this last time too. Okay, there's something like this where you have a lone pair and 2 orbitals, or 2 double bonds, and then you have another object and then the last so you could be faced with any one of these. Sorry, hold on, let me draw my. So you could be faced with any one of these situations. You could be given all 3 of these molecules and he could have you say whether or not they're aromatic or why they're not aromatic. And a lot of times with these lone pairs, we have to make sure whether or not the lone pair is in the pi system and if it can contribute to the conjugation of the molecule. So for example, this one, it can because of resonance, so we can draw resonance structures that bring this around, and so we can know this is aromatic. But with this one, because we're already conjugated, and then we already have our orbitals in such a way, this set of lone pair, this lone pair cannot contribute into the pi system. And then same thing with here. It's important to see that while we have 2 lone pairs, it's important to be able to just be like, okay, which one's going to contribute, which one's not. At least one will contribute and the other one won't. And it doesn't matter which one is which. Just make sure you have one contributing and another one not. Okay, yeah.
So do each of those have 6 pi electrons?
Right here? Yeah, so each of these would have 6 pi electrons, yeah. Any other questions? Yeah.
You have a carbon cation. In the example you did earlier, you had 2 pi bonds, and then a carbon cation, and that 500 maybe. It was.
So like that, and I had something like that.
Yeah.
Yeah.
So is that aromatic?
Well, so let's see. So it's obviously planar conjugated. So no, this would not be aromatic. No, because it breaks Winkle's rule, so this would be anti-aromatic. But if I replace this with a lone pair, then it would be aromatic. Yeah.
I just had a question about the practice exam, about a specific structure which I don't understand why it is aromatic. Can you explain it to me really fast? It's a cyclobutene with 2 positive formal charges on it.
So something like this
That would be on the same side.
on the same side,
And then the double bonds opposite, yeah, over there.
like that.
So it says that that is aromatic, but I thought that Professor Price said that you cannot have 2 positive formal charges next to each other.
Well, I mean, what I can do is I can draw resonance, and then I can just delocalize one formal charge around. And so, remember with resonance, this isn't what the molecule actually looks like. It's like a conglomeration of all the resonance structures
Yeah,
together.
it's like it's conjugated on the interior, I guess.
So it's conjugated, it's cyclic, and then if we say, well, this,
Yeah.
yeah, so then divided by 4, n can equal 0, so yeah.
But I'm just confused at that because yesterday I thought you said that having 2 positive or having 2 formal charges next to each other would have made any compound 2 unstable.
Yes, but then that goes back to resonance. So with the other, so we were talking about like when we did reactions, like substitutions and such in chapter 18, right? And that's, yeah, because what happens is that resonance structure, it'll eventually come to a point where it can't. Like it'll get stuck, like they'll become so close together that it'll, because the reason is when we have that like set up the way it is, we don't have an aromatic compound, right? Because we don't have a fully conjugated system. And that's why it's an issue with those types of reactions, because first of all we've broken aromaticity, so now it's already less stable than it was before. And then even though we have resonance and it's delocalizing around, eventually it comes to the point where we put those 2 positive charges together, and because it doesn't have that aromaticity that this thing does, it destabilizes it even more. Yeah.
Isn't that still like an incredibly
Oh, this is very unstable,
like,
but it's still
it still fits like the criteria.
Oh yeah, this will like change in an instant, but it's still considered aromatic while the others weren't aromatic.
I guess that's, yeah, I guess that answers my question.
Yeah, I think that's my. Does anybody else have any questions regarding that? Okay. And then these are practice problems that you guys can go through, and then here's one last one for the test. So.
Alright guys, we're almost done. I'm so proud of you guys. So much school. It's so late at night. Alright, we're almost done. We'll be quick. Okay, so half of this stuff we haven't even gone over in class, which is why I'm saying we're going quick. He gave me his notes, so I just like took pictures of them and put it on here, and I have a few things that I want to say about them, but I'm not going to go in super detail because he's going to go over them in class. Okay? But still feel free to ask questions if you need to. Okay, so chapter 18 is all about electrophilic aromatic substitution reactions. Okay? Where the benzene ring is acting as the nucleophile, and you need a very reactive electrophile to be attacked by the benzene. Because the benzene is very stable and it's not going to attack unless it really, really has a lot of energy to push it that way. And then you need to restore aromaticity afterwards. Okay? So those are going to be the basic steps that you take every single time you do one of these. Okay? So, aryl halogenation, we went over that in class already. You take a halide molecule, Br2 or Cl2, and you react it with the Lewis acid first, which is always Fe bonded to 3 of the matching halide. So Br2 is going to react with FeBr3, and Cl2 is going to react with FeCl3. So they have to match. What occurs is the halogen molecule comes and attacks the iron and creates this complex. This part is a very good leaving group. So the benzene comes and attacks the bromine, and this leaving group leaves. Okay. You can also consider the leaving group leaving before and just leaving a bromine positively charged. Same concept. Okay, nitration is where you're taking an HNO3 and reacting with an H2SO4 to create a positively charged nitrogen, or, oh no, as you can see right here. Oh no. I just think that's so funny. Okay, so you generate the electrophile by protonating this OH group on the HNO3. And as you remember from 351, anytime you have an H2O bonded to a molecule, it's a very good leaving group, it's going to leave. Okay? So that leaves you with oh no. This is so easy to remember, I love it. So if you're left with oh no, it's positively charged nitrogen, the benzene goes and attacks the positively charged nitrogen, and then you rearomatize. Okay? That's nitration. Questions? Okay. Sulfonation, you also react SO3 with H2SO4, but when you protonate one of the oxygens, you're not going to make an H2O group, so it's not going to leave. But you're going to be able to introduce a positive charge through resonance to the sulfur, which then that makes a super exceedingly good electrophile. And then the benzene comes and attacks, rearomatize, there you go. Okay? Friedel-Crafts, alkylation. With this one, an alkyl group, either a tertiary, secondary, or primary alkyl group, bonded to a chlorine or a bromine, reacts with AlCl3 or AlBr3, and creates this complex. Okay? If it is a primary carbon, like this one, the complex stays together until the benzene attacks, and then this leaving group leaves. If it's secondary or tertiary, then this molecule is made, and then the leaving group leaves prior to the benzene attacking. So you create a carbocation here.
However, what do you remember about carbocations from 351? They rearrange. So if they're going to rearrange, they will. If you have a secondary carbocation and there's a tertiary carbon in that molecule, it will rearrange to there and then make that bond with benzene. Okay? So you have not lost these. They're still important. Please always remember them. And then you can see this mechanism in the text if you'd like. Acetylation is where you're binding this double bond O to a carbon. You're binding this whole group to the benzene. Same thing, AlCl3. You have a Cl bonded, make the leaving group, and then you attack once the leaving group has left, and then positive charges on carbon. Okay? So it's pretty familiar. All of these are basically the exact same steps over and over. You're just, the steps in making the electrophiles are different every time. Okay. Electron donating groups versus electron withdrawing groups. If you have an electron donating group, it's an oxygen or nitrogen, and they donate by resonance because they have lone pairs that can donate electrons into the ring. You also have inductive electron donating groups, which is alkyl groups, because a CsP3 carbon is less electronegative than a CsP2 carbon. So a CsP2 carbon will pull electrons from a CsP3 into the ring. However, if you have a difference between a resonance and an inductive electron donating group, the resonance one will take precedence when directing which substituents, where the substituents will add. And then you have electron withdrawing groups. You have resonance electron withdrawing groups, which is an atom bonded to the benzene and then double bonded to a more electronegative atom than it. So that's why NO2 is an electron withdrawing group, because nitrogen is double bonded to oxygen, which is more electronegative than it. Now here's a kicker. You would think that halides would be electron donating groups because they can resonate into the ring, which is true. However, they are more electronegative. They are the most electronegative. If you can see, fluorine, bromine, they are the farthest to the left, to the right, which means they're going to be the most electronegative, and they are going to have a stronger inductive effect than a resonance effect. Okay? So because of that, they are going to be electron withdrawing groups. However, they still direct, like a donating group, which is what we're talking about here. So electron donating groups and halides will do ortho and para directly. And resonance electron withdrawing groups will do meta. And I would also remember there's a question on the practice exam about acidity, which benzene ring was more acidic. The electron donating groups will increase electron density into the ring, which will increase their reactivity as nucleophiles or bases. And if you have a stronger base, that makes its what? Acid. Sorry, I just swore on camera. Anyway, it makes its acid what? Weaker, right? So if you have a stronger nucleophilic benzene from electron donating groups, they're going to be less acidic. Okay? And then if you have electron withdrawing groups, they decrease the electron density within the ring, which decreases the reactivity of the nucleophile or decreases its basicity. And if you have a weak base, you have a strong what? Acid. Okay? So make sure you can reason through all those trends as you're taking the exam. Also, I just wanted to make a plug for this as well. Mavin, if he talks about it in class, I would just remember it because he loves it. If he doesn't talk about it in class, I wouldn't worry about it. It's just application to benzene chemistry. Okay, we're done. Good work, you guys. If you have questions, you can come and ask us. And I'll email out all this stuff to you guys tonight, hopefully.